Here's the introduction. The setup is that I held the head of the slinky to make it stable, and then I released the slinky from rest. The aim of this lab is to predict the motion of the end of the slinky. The result is that the end of the slinky stayed still until the top part reached it. Here is the physics principle. The first one is Newton's second law. Net force is equal to rate of change of velocity times mass, and the net force is the sum of gravitational force, tension given by the slinky, and the drag force. Gravitational force is negative mass times gravitational constant times j hat, and drag force is negative b constant times speed squared times v hat. And then let's look at tracker. I track the end of the slinky, and notice that initially the end of the slinky stayed still, and then the top part reached it, and then they fell together to the ground. And here is the data, here is the actual graph. And then let's look at my code. The mass of the ball is 0.25 kilogram. I got that data from the internet. And the initial position, I got that from the first line of the tracker data. The initial velocity is 0. And I experimented with this b constant to make the experiment line and the data line and the model line match at the end. For t smaller than 0.99, the end of the slinky stayed still, so we assume that the net force is 0 for that period. This is the gravitational force, and since the net force is 0, tension is just negative gravitational force. And here we do not have the drag force. That's because the end of the slinky is still. Here is the Newton's second law to predict the motion. And for t greater than 0.99, the gravitational force is the same. We do not have tension anymore because the slinky is compressed at the greatest amount. And here is the drag force. The net force is just the sum of the gravitational force and the drag force. And here is the Newton's second law to predict the motion. And let's run this program. Here is the data, and we can notice that the graph is similar to the one on the tracker. And I put all the data to a spreadsheet. Here is the chart. Before t equals to 0.99, there is a little discrepancy between the two lines. That's because we assume that the net force is 0. However, in reality, the net force may not be exactly 0. And the discrepancy after that is relatively bigger. That may be because the video is of poor resolution, so I didn't track the end of the slinky pretty well. And the b constant is great. That's because the two lines match pretty well at the end. And let's look at the conclusion part. First, I want to summarize how to predict the motion of the slinky's endpoint. I divided the video into two parts, and then I calculated the net force for each part, and then I used Newton's second law to predict the motion. And the result is that the end of the slinky stayed still until the top part reached it. Here are the improvements. I want to track the motion more accurately by making a video myself, so that the video can have high resolution, and then I can track the end of the slinky better. And also I can have more accurate data. I will know what exactly the mass of the slinky is instead of getting the data from the internet. Thank you.